nanohub.org.
So the lecture is on a closer look at the quantum harmonic oscillator. If you have just walked in, I'm guest lecturing for Erica. My name is Dr. Iyer Biswas or Shri or Srividya, whatever you want to call me. Just call me by whatever is comfortable for you. Okay, let's get started. Recall the classical harmonic oscillator. Are you able to read fine from the back? So a quintessential example is mass attached to spring. Mass m attached to a spring with spring constant k. As you know, potential energy is does this sound right? Half kx square. Okay, so potential energy is half kx square. Newton's laws. d2x dt square is, let's start with force, is minus kx, corresponding to this potential energy. So we can write down and d2x dt2 is minus kx from here. And the solution, x of t is a sine omega t plus b cosine omega t, the familiar simple harmonic oscillator, where omega is the classical angular frequency of oscillation, which is clearly related to the spring constant through this, or omega square is equal to k by m. Everybody more or less with me on this? That's the classical version. Why do we obsess so much over the harmonic oscillator? If you feel like you've seen enough of it in this course, rest assured, if you stick with physics, you'll be seeing a great deal more of the harmonic oscillator. We are just getting warmed up. Why? Why do we obsess so much over the harmonic oscillator? I will expect more participation going forward, but since it's early in the lecture, let me give you the answer. Consider a generic potential. So, sorry, generic V of x. Etc. And let's focus on some local minimum. And consider a parabolic approximation to this generic potential around the local minimum. Why are we considering the parabolic approximation? Well, for those of you who like to think in terms of algebra rather than pictures, let's expand, Taylor expand V of x around x naught, the local minimum. As you know, this is constant term plus linear term the linear portion, plus half second derivative times quadratic term, etc. This is a potential energy. This term is constant. As you know, it doesn't do anything interesting because it doesn't change the force. X0 is a local minimum, so what's this term?
0.
Louder?
0.
0. Please clap for this gentleman. And what's your name, sir?
Pratyush.
Pratyush. Thank you, Pratyush. Not just for answering correctly, but for answering at all. And what about the second term? It's our first non-zero or non-trivial term, and it's quadratic in x minus x0, and that is this parabolic approximation. Everybody remember parabola goes as x squared? Parabolic. And that is why we obsess over the simple harmonic oscillator. Because this potential energy form is what you get if you take any generic potential energy and expand around the local minimum. This is the leading order term. Good? So are we a little bit more invested in the simple harmonic oscillator, knowing that it's not just some esoteric thing that physicists like to pull out all the time, but it actually is practically useful all the time? Okay. To summarize, any generic v of x for small enough x minus x0 is approximately equal to half second derivative at x0 times this quadratic term. So we can identify this second derivative at x0 term with the effective spring constant. Here. Okay, that's the spirit in which we are approaching the harmonic oscillator. So that was lightning introduction in the classical version. But now we go to the quantum version. For the quantum version, as you know, the thing we need from here is the form of v of x. Quantum analog. V of x, we had half k x squared, and we also discussed what omega was, the angular frequency, in terms of k and m. For the quantum analog, it's convenient to write this potential in terms of m and omega. This is how I want it. Yeah. M is mass, of course. Omega is now to be understood as the classical angular frequency. It's just notation. Because you may not always have a spring connected to a mass as the physical instantiation of the potential. Okay? So this is just setting up our language to talk about this harmonic oscillator now within the quantum framework. Shall I proceed? At this point, let me pause and ask you if you know the drill for given a potential, how do you do quantum mechanics with it? I know you do because I've seen the lecture topics that Erica has gone through. but I am going to, without writing the prescription down on the board, because it won't be directly useful for this lecture, just go through the prescription for how you're expected to treat a quantum mechanical system given the potential with you, and you can nod with me as we go through each step. Okay? Candle, does that sound like a plan? As you know, for a generic problem, given the functional form of V of x, we assume it's a time-independent potential. In this course, you're only going to meet V of x. Given the initial condition, capital psi of x comma 0, so you're given V of x and initial condition, the problem is to find capital psi of x comma t. Capital psi is a solution to the time-dependent Schrödinger equation. The typical strategy is to solve instead the time-independent Schrödinger equation, which yields a set of solutions, small psi of x, each with associated energy, E1, E2, E3, etc. And then our strategy is to write the initial condition, capital psi of x comma 0, as a sum of terms, C1 times small psi 1 of x plus C2 times small psi 2 of x and so forth. And then to find these coefficients through magic using the Fourier trick. And then, are you still with me? Should have done this drill a few times by now. And then once you have those coefficients, it's trivial. You just tag on the phase factors and get your general solution. Does this sound vaguely familiar? The good news is that we are not going to do this brute force technique for the harmonic oscillator in class today. It can be done, but what I want to walk you through is a diabolically clever alternate way of arriving at the same answer, which you will only fully appreciate if you sweat your guts out through the brute force method afterwards. So will at least some of you take that on so that you can appreciate the full beauty of this alternate technique for the harmonic oscillator? Yes? Okay. All right. With that background, and having declared that we will not take the brute force route, what we want to do is a clever solution of the time-independent Schrödinger equation. That's what the rest of the lecture is about. And you've also seen some of this, but I want to walk you through the nuts and bolts in detail. Okay. Everybody remember the time-independent Schrödinger equation? Let me write it down. So we have the potential energy term. Time, I'll write it once, and then I'll independent Schrödinger it's laborious to write this again and again. So going forward, I am just going to write this. Okay? The time-independent Schrödinger equation is minus h bar squared by 2m d2 small psi dx2 plus v of x small psi of x equals e times psi of x, to be determined given here and also to be determined. Everybody with me? This is not a grim topic, even though it seems like it right now. the material we are going to cover in today's lecture, if you were to ask me, could easily go into centerpiece in Museum of Amazing Human Thought or Human Achievement in Thought. It is an extraordinary set of ideas that come together to give you the story that I'm telling you today. And even in an hour and change, I am hopeful that you'll feel the wow of human accomplishment here. So stay with me. We'll get there. So here is the time-independent Schrödinger equation, which I'm going to call this from going forward. The program is to find small psi of x given the potential energy term, which is quadratic in x for the simple harmonic oscillator. Okay? And corresponding to psi, you also need to find E. And typically, we expect an infinitum of solutions, psi's with corresponding solutions E. Have you seen this before for, let's say, for what potential have you seen this before besides the harmonic oscillator? The well? Okay, the infinite well. Yep. So you know the drill. So instead of the brute force technique, now we want to try a clever technique to solve for the infinitum of size and ease allowed for this problem. And to motivate the method of solution, let me first clean up this equation as follows for the simple harmonic oscillator. So to start with, we write the time-independent Schrödinger equation in a more suggestive form. One by 2m times p operator square plus m omega x operator the whole square operating on psi equals E psi. Where, as you know, p operator is h bar by I ddx. Is this familiar? And so p square is minus h bar square d2 dx2, and x is just x. We must treat operators with tender, loving care, gently, because operator A times operator B need not be equal to operator B times operator A. Okay? And we'll see this explicitly as we go forward. Is this vaguely familiar to everybody? Okay. So take this hat notation seriously. This is just to remind ourselves that if another operator multiplies it, we must preserve the order of multiplication. So if this is on the left and something else is on the right, we want to keep it that way and not flip the order cavalierly. Okay. You know what this operator is? Anybody? Take a wild guess. Yes. Indeed, the Hamiltonian operator. So in fact, we could have tersely written the time-independent Schrödinger equation as this. The reason this is a suggestive form is because if we were to think about the number analog for what we have Now in operator form, let me tell you what I mean by that. Think about the algebraic identity, u square plus v square. Can anybody factorize this for me? Yes. Go ahead.
U plus vi and u minus vi.
I think you said u plus iv plus u minus iv.
Yeah.
That is correct, but I just want to be slightly different and write it as iu plus v times minus iu plus v, which is also equally valid, right? Everybody with me on factorizing this? In that spirit, we will attempt to factorize the Hamiltonian. Okay. But can we do that, given that p and x are operators and may not elegantly allow us to write it in this kind of neat factorized form? That's the question. So take a deep breath, because that's what we are going to do for the next several minutes. Attempt to factorize this Hamiltonian in the spirit of that algebraic identity. So so we are now in the hard slog part of the hike. Scenic views will come, but you have to stay with me through this. Is the motivation clear? We are going to attempt to factorize this Hamiltonian, which has these two quadratic terms, which have operators in them, in the spirit of that algebraic identity. Okay, let's get started. To sort of clean up notation, I want to introduce, let's examine operator A plus, defined as, stay with me and I'll motivate why we are doing this, some factors in the front, 2h bar m omega under square root, times, this is the important part, minus I p operator plus m omega x operator. And its analog, a minus operator, which is same prefactor in front, which at the moment you can just take down as something that we have put in the front to make a future result look nice. Okay, but that's not the important stuff. Times the analogous plus IP plus m omega x in the spirit of this relation. Okay, and so you won't be surprised that the next thing we want to examine is the product A minus operator times A plus operator, which at least in spirit looks like this. Are you with me? Okay, hard slog coming up. Take a deep breath. Here's the definition of A plus, comes with a negative sign here. Here's the definition of A minus, comes with a positive sign here. We want to multiply in the order this times that. Okay, A minus times A plus. So let's do that. The prefactors under square root multiply with each other, getting rid of the square root. 1 by 2 h bar m omega times, let's write it out, IP plus m omega x times minus IP plus m omega x. So straightforward to do the multiplication, provided you remember these are operators and need to be handled with care. And so what stays on the left stays on the left, and what stays on the right stays on the right. Okay? So this becomes p square plus m omega square plus m square omega square x square. Those are the easy terms. And now come the terms we have to handle with care. I minus I m omega minus I m omega times x times p minus p times x. Is my algebra sound? You're getting the same thing? This thing, as you may have seen before, is written in shorthand form as this, where this notation stands for something that's referred to as the commutator. Have you heard this before? And so, to proceed further, we need to find the commutator of x with p, which, even though I expect you know from before or you've seen before, I'm going to quickly evaluate for you, just to get you warmed up with operators. Okay? Do I belabor the point? Handle operators with care. To find out what this is, if you were to calculate this, I would highly recommend sticking in a test function here to evaluate what it's equal to, and in the end, the test function will cancel off. So let's do that. This is x times h bar over I d dx of f minus h bar over I x times f. So that's h bar over I times x df dx minus, from here you're going to get two terms. So that's x df dx, cancelling off with this, minus f. Quick reminder, I square is minus 1. So minus I is the same as 1 by I. We have a 1 by I here and a minus here. So we are left with I h bar times f. Compare. So we end up with commutator of x with p is I h bar. The famous canonical commutation relation. With me so far? This should be old stuff. And the reason that we got into this is because we are trying to evaluate this product, because we are trying to write the Hamiltonian in a factorized form in the spirit of this relation, and we were stuck at a point where we needed the commutator of x and p. The hard slog part of the hike is almost done. Okay, scenic views are coming up, so please stay with me. So now we take this and stick this in here and see what happens to this product, a minus a plus. Continuing, a minus a plus is therefore equal to what we had before, one by 2 h bar m omega times this stuff just what we had before. Minus I by 2 h bar. Just opening up this bracket. You have a 1 by 2 h bar m omega here and a I m omega here. M omegas cancel off. Minus I and 2 h bar. Minus I 2 h bar times the commutator of x comma p. This will be a lot more fun if you actually work it out with me. If I'm talking at you, I don't know, maybe meh. Don't feel pressure, but scribbling along with me, you may have a lot more fun. Okay, so we are going to substitute for this. We just derived what this is. This is IH bar. IH bar. Kind reminder, I square is minus 1. I minus sign. So we can clean this up. What do we get? 1/2. Through a derivation like this, it is a relief to know that somebody is paying attention. So please follow along with me and yell out answers as I ask for them. We are almost at the end of this one. Okay, of this one. So we conclude. A minus A plus, which is what we started out with, is p square plus m omega x whole square divided by 2m plus half. What's the first term?
Kinetic energy.
It's got p square, sorry, by first term I should be clear. What's this term? Louder?
Hamiltonian.
The Hamiltonian. The p square by 2m part was the kinetic energy part, and this is the potential energy part. So together the Hamiltonian. So we have rewritten the Hamiltonian in terms of the product A minus A plus as,
It's a factor of H bar.
yeah, I'm searching for it actually. Oh, from here. So we've rewritten the Hamiltonian in terms of the product A minus A plus as the Hamiltonian is H bar omega times A plus A minus minus. We have a minus sign problem. Okay, this is what happens when we try to do too many steps in one shot. Give me a moment to remind you what we had. We had minus I by 2 h bar here. Minus I by 2 h bar. And then we multiplied that by I h bar. And so we got rid of this and we got a plus sign. Ah, my bad. We are doing fine. Okay, we are doing fine. A minus A plus minus half. Okay. So let's summarize what we have found because we'll use this again and again. The Hamiltonian is A minus A plus minus half times H bar omega. Analogously, instead of starting with the product A minus A plus, we could have started with A plus A minus, following through the derivation in exactly the same way. You would have actually gotten this commutator with a different sign, and so forth. So you will find you could also write this as H bar omega times A plus A minus plus half. So there's a minus here, and you would get a plus here if you did the complementary derivation with A plus A minus. Still with me? Okay, what's the big deal? Well, before we start unpacking all the wisdom that's contained here, and again, I'm hoping to convince you in the next 35 minutes that this is an extraordinary accomplishment in the Museum of Human Thought. So stay with me. There's a lot to unpack here. But the next thing I want to calculate before we actually unpack that result is the commutator of A minus and A plus. We are almost there, because the commutator, as you know by now, is just this difference. Are you with me? And from here, you can do the math in your head. What is it? Just 1. It's to get this nice result of 1 rather than some yucky factors on the right-hand side that we chose these prefactors before. So this result, that the commutator of A minus and A plus is 1, will turn out to be useful. So let's put that up here. And I just remembered what I wanted to point out to you earlier. What units does H bar omega have? Energy, indeed. Hamiltonian units of energy, H bar omega units of energy. What is the unit of the product A minus A plus? Stare at the formula. Energy on the left-hand side for Hamiltonian, energy for H bar omega. What's left over must be dimensionless. So the product A minus A plus is dimensionless, which also squares with commutator is 1, because 1 is dimensionless. So dimensionally, all of this makes sense. We haven't dropped any factors by accident. Okay? All right. Now that we have these, we are ready to start constructing pictures. So this is just cosmetic, but stylishly you can combine these two relations into one as Hamiltonian equals H bar omega times A plus A minus plus half. This is one of the relations. And then you can write the second relation right here. And if you see a formula written like that, that means either you consistently read the top line or you consistently read the bottom line. Yes. So sometimes you'll see those two formulae written like this, and that's what that means. Is everybody with me still on the science? Okay, so for the rest of what comes, we will have to make clever choices of which of these two equivalent formulae for the Hamiltonian we want to use for the time-independent Schrödinger equation. Okay? So both are equally valid, but one route is the scenic route and the other one is the slog route. So I'll motivate you through the use of this formula again and again over what comes next to appreciate better what the A minus A plus operators do for us. Here is the crucial argument in this lecture. Claim. If psi satisfies the time-independent Schrödinger equation with energy value E, it's a lot of words that basically says if H psi equals E psi, that's what we have so far, Then, here's the claim. So does A plus psi, but with energy value E plus h bar omega. That is, if psi satisfies the time-independent Schrodinger equation with energy E, then A plus psi satisfies the time-independent Schrodinger equation with energy E plus h bar omega. So if this, then this. As you can intuit, this is one of a pair of analogous results. We could write the analogous result for A minus. And let me also write that statement. And since that proof will be very similar to this one, I'm going to do one of the proofs for you and leave the other proof for you to try at home. This treatment is taken out of the marvelous textbook by David Griffiths. Are any of you familiar with this book? And I used the second edition. I believe the edition that's out there right now is the third. I cannot imagine that something profound has changed for what I've told you. Okay. So the analogous result, or the analogous claim, which I'll also write down, is, well, hold on, let's do this proof first and then I'll write down the analogous claim. So let's start with H times A plus psi, which is what we have here. We want to show that it's equal to this, given that psi and E, given that H psi equals E psi. So starting with this, we can unpack using an appropriate choice of formula for Hamiltonian from one of these two. And I am going to choose this one, and I'll tell you why in just a moment. So I chose the top line. So this is what I have substituted for the Hamiltonian. And this is as before. Remember, we have operators, so we treat them gently and keep the order of multiplication the same. This is on the right-hand side, and we want to bring it in. So let's do that. H bar omega times A plus A minus. And now we are going to stick in the A plus on the right-hand side, plus A plus divided by 2 from the second term. With me so far? And now we pull out the A pluses to the left. That's a legit operation. Are you with me? I'm not changing the order of multiplication. So this is H bar omega times, now we pulled out the A plus to the left, times what's left over here is this, A minus A plus, plus once again half. Now I want to flip the order of this, but I have to pay a cost, and that cost is given to me by the commutator. Because the commutator, so let's unpack this relation again. This relation is telling us A minus A plus minus A plus A minus is 1. I want to trade A minus A plus for A plus A minus. So I have to rewrite A minus A plus as 1 plus A plus A minus. Are you with me? Almost there. This is H bar omega times A plus times, flipping the order, a plus, a minus, plus 1, and then the half from before. And we got this from the commutator, which we unpacked as this. Almost there. H bar omega is just a number, regular number, not an operator. So we can freely pass it through operators. Are you with me? So we can bring this in here and then take it inside. So what we in fact have is Hamiltonian. Sorry, we have to keep track of this A plus. So A plus times the H bar omega passes through, and this term combined with this term is once again just the Hamiltonian. Read the top line. And then what's left over is H bar omega multiplying the 1. I'll write it down and then you can take a deep breath and stare at it. And then what we had from before is the psi. Almost there. Do you agree with my algebra? Any questions? H bar omega is just a number, so we passed it through and multiplied, and identified two of those terms with the Hamiltonian, identifying with the top line of that equation again. What was left over was 1 times H bar omega, which gives me that second factor of plus H bar omega inside the bracket. And now we do the clever thing of multiplying this with this again to get number times psi rather than operator times psi. So but this is a number, so we can bring this here. So this is just E plus H bar omega times A plus psi. Proved. All of a sudden, we have arrived at physics from this extremely dry algebra. And the physics is this. If psi satisfies the time-independent Schrodinger equation with energy value E, so does A plus psi, but with energy value E plus H bar omega. And for this reason, the A plus operator is referred to as a raising operator and is one of a pair of ladder operators. Have you heard these terms before? And the other analogous result is the proof. This is one of a pair of analogous results, and the other result is, as you can possibly guess, if psi satisfies the time-independent Schrodinger equation with energy value E, then so does A minus psi, but now with energy value E minus H bar omega. And for this reason, the proof is very similar to what we just did. You would just use the other formula for the Hamiltonian to do it conveniently. Are you with me? And I strongly recommend going home and trying this. What's the worst thing that can happen? You'll probably not watch a video you would have watched otherwise and lose 20 minutes doing this instead. Since we are doing ancient math for fun today, you might as well close this out and try these things out at home at least once. We are almost at something very beautiful. We are ready to construct a picture. what these two results are telling us is that somehow, through magic, if you happen to have one state psi and the corresponding energy E for this problem, so you just happen to have this, then you can solve the full problem, because you can then construct the next state with the next allowed energy value by just operating the raising operator once, and the next state by operating the raising operator another time with corresponding energy value E plus 2h bar omega, and so forth. So on this side, you can climb the ladder through A plus, and on this side, you can climb down the ladder by operating the lowering operator and correspondingly lowering the energies as follows. So you could climb down the ladder with a lowering operator. This is fantastic, but problematic. Why is this problematic? Are you saying that the problem is that we are only allowed to climb rungs which are h bar omega or multiples of h bar omega different from each other? That's not the problem. That is, in fact, the quantum in quantum mechanics, which is that the energy is quantized. And so there are these discrete allowed levels, which for the quantum harmonic oscillator, it so happens, are equispaced. So that's not the problem. The problem is that, yes?
We don't have a ground state, like low.
Why do we need one?
Because like maybe you'll end up with like a negative energy, and that's not like.
You're close, but what's wrong with that? Almost there. And there's a very cute argument, which I want to give you in 2 minutes, which is quite useful to understand why what you're saying is true. Okay? So, theorem. E must exceed the minimum value of V of x for any quantum mechanical problem. E must exceed the minimum value of V of x for normalizable wave functions. Can you prove this to me in a couple of sentences? In the interest of time, I'll give you the proof. This is a deep statement. We are making a general statement about any potential. And then we'll also apply it to this problem, which will get us to what this gentleman told us. Pratyush? Rewrite the time-independent Schrodinger equation through trivial rearrangement as d2 psi dx2 is 2m by h bar square times vx minus e times psi. Okay, that is psi double prime is positive number times this thing times psi. Let's interpret this equation in a figure. Since we have second derivative is positive number times this times the function, if E less than V min, meaning if this term in the brackets is positive, then psi double prime and psi must have the same sign. Are you with me? I'm just reinterpreting the time-independent Schrodinger equation. Since this is a positive number, if E is less than V min, that would make this positive. This and this will have the same sign. What does that mean in figures? In figures, that means that psi must be like this, always bending away from the x-axis. Do you see why? Consider, let's say, this portion. If psi is increasing with x, and its slope is increasing with x, then you get a function of that form. So psi and psi double prime both have the same sign here. And the rest of the shapes follow from symmetry arguments. So let's step back. If E is less than V min, then psi has to always curve away from the x-axis. But what's the problem with such a psi? If it never curves back down as x goes to infinity, you cannot normalize this. Right? Psi has to go to 0 as x tends to infinity for it to be normalizable. And so we have proved our theorem. E must exceed the minimum value of Vx for normalizable psi. Are you wowed? You barely needed high school math to make this argument, but it's deep physics. And so we conclude that we have a problem with this ladder because our potential energy was half m omega square x squared. What's the minimum value for this? 0. The minimum value of our potential for the harmonic oscillator is 0. So surely I cannot indefinitely keep climbing down this ladder because it has to be capped at the bottom. There has to be a lowest energy state with energy greater than 0 for this theorem to hold. What gives? Its energy must be greater than 0, must exceed.
Yeah, so that's why.
Oh, sorry, you were saying, say that again?
Were you asking why can't the number can't be 0?
No, how do we fix the ladder is the question. The ladder allows you to climb down indefinitely. That seems logic. We just derived this. But theorem says you can't have well-behaved wave functions if E is less than V min. How do we reconcile the two? Our ladder picture was constructed from theorems which did not guarantee that the size we would construct by raising and lowering the original well-behaved normalizable size would themselves be normalizable. Let me say that again. You can start with well-behaved normalizable psi, and as you apply the raising operator, the theorem doesn't guarantee that the new wave function you have created or new solution to the time-independent Schrodinger equation you've created is itself normalizable. It only says that it solves the time-independent Schrodinger equation. So normalization is not guaranteed. Are you with me? By the same token, as you climb down the ladder, you have to check if the new solutions you're creating are normalizable. And what this theorem is saying is that at some point, you will hit a non-normalizable solution, which will correspond to the which will give you, not correspond because it's, which will give you the lowest rung of the ladder. Let's see how that works. The lowest rung of the ladder will in fact, okay, maybe there's one more point that's worth unpacking before we do this. What does it mean for psi to be non-normalizable? What are the options? How can you end up with non-normalizable psis? If psi is identically 0, right? Because then you can't make the area under the curve for mod psi square equal to 1, which is what we need for decently behaved probability densities. So one option is that psi is identically 0. That's non-normalizable. Another option is that mod psi square is infinity. It turns out in this case, we get the lowest rung of the ladder by looking for non-normalizable psi's which are identically 0. So in fact, that gives us the following relation. If you try to climb down below the ground state, you hit a non-normalizable solution. Is the argument clear? So see, we have not only fixed the ladder, but in fact completely solved the problem. You don't see it yet, but you will in 2 minutes. To construct this ladder, I needed to magically have E and psi given to me, and then I could construct the rest of the ladder. But now, I have a relation that is going to give me the ground state. So I will have, when I'm done solving this, the lowest rung of the ladder and the corresponding energy. And then through this process, I can construct everything else, because we already know how to do that. So no magic needed to get this pair. We have this. Okay? So just a little bit algebra left to unpack this, and then we are going to finish constructing the ladder and solve the problem and go home. Here is A minus. We need to operate it on psi naught to figure out what psi naught is. Conveniently, the right-hand side is 0, so we can forget about this prefactor. So we just have I times P operator, which as you know is h bar over I times d dx, operating on psi naught, plus m omega x operator is just x, is 0. This is a trivial differential equation that all of us can solve without any help from computers, right? You'll see in a moment. This is just d psi naught over psi naught equals minus m omega divided by h bar times x times dx. I've just rearranged. This gives us psi naught of x goes as, you're going to get x squared over 2 here, and then we have to exponentiate because you'll have a logarithm here. And so psi naught goes as e to the power of minus x squared with the prefactor m omega by 2 h bar, which is a Gaussian. So you can look up integral tables to figure out the prefactor, or just do the normalization yourself to figure out the prefactor. Doesn't matter what it is, some prefactor which is given by normalization. We have psi naught, and the ladder stops at psi naught. So we've cleaned up this picture. This is now psi naught, and we know how to construct everything else, provided we have E naught. How do we find E naught? Almost there. We go back to our dear friend, the Schrödinger equation. And make a wise choice for the Hamiltonian again from the relations I've erased. We in fact choose h bar omega times a plus a minus plus half operating on psi naught equals E naught psi naught. You can check this in your notes that I got this right. And the reason I chose this is that conveniently a minus operating on the ground state gives us 0. That's how we identified the ground state. Correct? So this term drops out, and you're left with h bar omega times half times psi naught equals E naught psi naught. Ta-da, you're done. E naught is half h bar omega. So we have solved the full problem. For completion, let me write down what happens when you take the pair psi naught and E naught and successively construct the first excited state and the next excited state and the next excited state and so on using the raising operator. You end up with, as you can directly read off from our ladder picture, En is n plus half h bar omega, corresponding to n applications of the raising operator to psi naught, for which we have an explicit formula. That's your psi n, with the caveat that you must remember to normalize at each rung of the ladder. And that's just the normalization constant. Solved. What we have go ahead, please, loudly. Once you go back home and process this and internalize this, I want you to appreciate at least some of the many ways in which we have derived some profoundly disturbing results about the harmonic oscillator, and see how you would close the gap between here and what we did in our lightning introduction with what the classical harmonic oscillator does. What's oscillating? It was very clear in the classical case what was oscillating. Where are the oscillations? Energy is quantized. Well, that's why it's quantum mechanics. What does that mean? What does it mean that the ground state has this non-zero energy half h bar omega? There are several physics courses over which these profoundly disturbing facets of this quantum result can be unpacked. But there are a few that you can try at home already. Are you familiar with the PHYS theorem? Is that how I say it? Let me write it down in case you pronounce it differently. I am sure you have seen this in a problem, even if you haven't learned to identify it by that name. It is a result that tells you how you recover the classical picture from the quantum mechanical version. I want those of you who feel motivated to take what you've learned today and extract the maximum physics for all the sweaty algebra we've done, to look up PHYS theorem and see where the oscillations can be recovered from. How do you recover the classical oscillator from this? One more thing to try at home and then I'll stop. You can now construct explicit expressions for, well, let me just stop with PHYS theorem. You can clap again and we'll call it job well done.